Okay, welcome to exam 4 essay 2 video. Today we're going to talk about the lungs. So first off, we're going to talk about the lung itself. Okay, so this is our lung right here. This is going to be our trachea. It's going to come and branch off into our bronchi. Eventually those bronchi are going to get into the lung, branch off even more into some respiratory bronchi, and eventually into our alveolus, which is just like a little sac-like thing, structure. Here I have drawn that there's like one big alveolus. That's not how it is. There's just lots of smaller alveolus throughout the lung, but we're gonna draw it like that. So that's our alveolus. We got a few different membranes that we need to know here. So this one that's gonna be right up against your lung there. Right up against your lung there. That's gonna be your visceral pleura. And then this one, there's going to be kind of another one kind of outside of it, represented by this green drawing here. That's going to be your parietal pleura. Okay, and then the space in between, that's going to be your pleural space. Okay, now I have drawn that they're kind of separated. That's not necessarily how it is. They're more like if you took two layers of saran wrap and laid them on each other. That's how the visceral and parietal pleura would kind of sit on each other. But what that does is it's like if we took our hands and kind of mashed them together, took kind of like a cupping shape, mashed them together, there'd be kind of that suction force there. So what that does is eventually, we're also going to have some lymphatic vessels that are going to be in here kind of sucking fluid out. So what that does is it creates a negative pressure in this pleural space. So it's going to be about -4 millimeters of mercury inside that pleural space. Now the reason we need that is because in your lung you have all these proteins, all these elastin proteins. So what that does is the lung's kind of lazy and wants to just spring back into like a softball size shape. Because of those proteins, they just kind of want to spring it that way. But we can't have that because we need to be able to get air into the lung. So this negative pressure, it makes this vacuum, let's say about -4, it can get up to like 8 or 10, -8, -10. And so what that'll do is it'll kind of pull that, kind of suck on that visceral pleura and kind of pull the lung out, which is very important for inspiration, for breathing in. Okay, because on the outside here, we're going to have just a like 0 ATM. Yeah, so we're going to have we need this pressure gradient. So we want air to be able to move into the lung. So that's why we need a negative pressure here, so that we can have that. So when your diaphragm and all those muscles for inspiration kind of work, it's going to make this more negative. It's going to pull on that even more. It's going to allow your lungs just to have that negative pressure, and air is going to be able to move into your lung there. Then for exhalation, kind of we relax, those muscles for exhalation will move, and it's going to make this pressure kind of positive, and it's going to be able to push that air back out. Okay, and even just relaxing, having it go back to that normal gradient is going to push some air back out, which is exhalation. So we need this negative pressure here in order to maintain a gradient, in order to breathe, to ventilate. I think that's all we needed for that kind of section there. Let me take a look here. Yeah, so we have those membranes that are going to kind of make that negative pressure and cause that pressure gradient for air to be able to come in and out. Okay, so you need that negative pressure here because out here is 0, so we need that vacuum-like pressure in order for our lungs to inspire good. Okay, so if we were to mess this up, there's something called pneumothorax. So if we were to put air into this pleural space and make our pressure go up, because there's like Boyle's law, which is like, oh, what is it? Anyway, but when pressure goes up, volume goes down. Is that right? Yeah, so pressure and volume, they're inversely related. So we're gonna have more pressure in here, which is gonna decrease the volume here. So it's gonna make it tough to inspire when we have this. So air's gonna come in, it's gonna make this pressure more positive, which is gonna mess up our gradient. We're not gonna be able to inspire very good. And then our lung is gonna collapse. It's gonna decrease in volume there. So this is called pneumothorax. And pneumothorax is just when air gets into that pleural space and messes up our negative pressure gradient. We can't have that. Like we said, the lung's lazy, it wants to just spring back. We need that negative pressure to suck it back and allow that air to ride that pressure gradient into the lung, okay? What else do I want to talk about here? So pneumothorax, air gets into the pleural space, messes it up. That would be like a normal pneumothorax. There's tension pneumothorax, which is when like somebody stabbed you, air's getting in, but then there's kind of a one-way valve. So the air gets in, but then it can't get out, which again, it just messes this all up and collapses your lung, which we can't have, okay? Okay, another thing we need to address here is in your alveolus, we're gonna have all these water molecules kind of lining it. Okay, so all these water molecules are lining it. Water molecules, it wants to form what's called cohesion, so they want to bind together. And that cohesion makes something called surface tension, okay? So this water forms this surface tension here. And we have something called Laplace's law, which is pressure is going to be equal to 2 times the tension divided by our radius here, okay? So what we want is we still want to maintain a pressure gradient in order for the air to get into the alveolus. But if our tension's high, then our pressure is going to be high, which is going to mess up the gradient, okay? So we could either make our radius bigger, make our alveolus bigger. So if our radius is bigger, then the pressure is going to be smaller. Radius is smaller, pressure is going to be bigger. But we just can't go into our alveolus and change the size of the alveolus. So really all we can affect is tension, okay? So we need to bring that tension down in order to make our pressure go down to have a gradient here. So what we use is something called surfactant, okay? So surfactant in your alveolus, let's draw another alveolus here. In your alveolus, you're going to have some pneumocytes here. So these are type 2 pneumocytes. Just do 2 pneumo. Type 2 pneumocytes, and what they have is they have a cortisol receptor on it. So things like cortisol, hydrocortisone will bind to that, and then they'll make something called surfactant. And surfactant looks kind of like a phospholipid. It's got a hydrophilic head and a hydrophobic tail. So it's got a polar head, non-polar tail. And so what that'll do is all these surfactants will bind and it'll mess up our tension of our water, so the tension will go down. And you'll be able to breathe. You'll be able to breathe in. So like babies, if they're right before they're birthed, that's not the correct word, but we're going to use it anyway. Their pneumocytes haven't activated and haven't produced surfactant. Until they get in there, they'll get stressed, their brain will produce cortisol. Cortisol will come bind to that cortisol receptor and produce surfactant. So then when the baby comes out of the womb, it'll have surfactant and it'll be able to take its first breath. But when this baby is born prematurely, before it has a chance to produce its own surfactant, then we have to give it like either an artificial surfactant or we have to give it hydrocortisone. The hydrocortisone will bind to the cortisol receptor so it can start making its surfactant in order to breathe. So that's the importance of surfactant. It's going to come in, it's going to drop our tension of the water to bring down our pressure so that we have that gradient and we're able to breathe in, okay? So that's surfactant. Let's see what else we need here. Surface tension. Okay, now let's talk about the alveolar gas law, which is this equation right here. So we have our alveolar pressure of oxygen is equal to our fraction of oxygen. So that's how much oxygen they're actually getting. So in the air, there's about 760 ATMs or torr. This might be torr. Either way, but there's, I think it's ATM. So there's 760 pressure of air, but only about 21% of that is oxygen. So when we do our math, 760 times 0.21 is equal to about 160 ATM. Okay, so this 21%, that's the fraction of the oxygen, or fraction of the air that's actually oxygen. So we take that and we plug that in there. And then we have our pressure ATM, that's just the atmospheric pressure, which is going to be our 760. So we plug that in there. Now we want to get rid of this pressure of water because we don't really care about the pressure of water. We don't want that to affect our equation here. So we need to get rid of the pressure of water, which is about 4750 ATM. So we'll get rid of that, and then we're going to subtract it by our arterial pressure of CO2, which is always about 40 normally, and divide that by our CO2 to O2 ratio. So R is going to be equal to PaCO2 divided by PaO2, and normally that's about 0.85. Okay. So that is how we're able to determine how much pressure of oxygen is in our alveolus here. And so clinically, if we have, let's see here, say someone has like a low arterial pressure, so normally it should be about like 100 to 104, say they have like a 90. So low pressure for oxygen messes up our gradient. They're not able to get as much oxygen to their tissue. So then we can say, well, in order to get this up, we need to put that patient on a ventilator, on a nasal cannula. We need to crank it to the max 29% in order to boost that up. We can also put that in here and see, okay, how much oxygen are they getting, which is this 21%. And then we can see, oh, well, what's messed up here? Like, what's going on? And then we could see maybe their CO2 is high. I think that would mess it up here. Anyway. But yeah, anyway, so we can kind of plug it in there and see what is off here in order to fix it. What's dropping this number down so we can fix it? So say, oh, well, we're gonna have to, maybe his pressure of water is too high, so we need to lower his pressure of water. Or again, his PaCO2 is too high, so we need to either increase this or lower this. So we just kind of use that equation to see how we can help that patient and get their oxygens up. So that's the gist for that. Okay, now let's talk about gas transport here. So again, this is our alveolus here, and then this is going to be our capillary, so just a blood vessel, this orange. And then this green is going to be a red blood cell. Now on our red blood cell, we have a protein called hemoglobin. Now we're going to talk about oxygen first. So essentially what happens, what we want to do is we've inhaled, so our alveolus has all this oxygen in it. So we have a bunch of O2. And what we want to do with that O2 is we want to get it into the artery, or into the capillaries, bind it to the red blood cell, and then transport it off to the tissue cell. And we're going to use that by gradients. So again, this PaVO2 should be about 104. And then we're going to have over millions and millions of alveoluses, this PaO2, so little a, again, it's gonna equal about 140, but what's happening is we're gonna have oxygen, and it's just gonna keep going through this loop. So really, the gradient here, there's more oxygen in your alveolus than there is in here, so oxygen is gonna wanna move into this artery. So oxygen is gonna come in there, and needs a pretty high gradient there. Oxygen is gonna come into this capillary here, and then it's gonna come and it's gonna bind to hemoglobin. And hemoglobin has 4 binding sites, so it can bind 4 different oxygens. It's gonna bind to that, so you get transported out to the tissue cells. And again, it's gonna kind of do that same thing. So there's gonna be a higher gradient in the red blood cell than there is our tissue cell. So this oxygen is gonna come off this hemoglobin and go to our tissue cell where it needs it, okay? So that's the story with oxygen. And so about 98% oxygen is bound to hemoglobin, and that's how it's transported. And then maybe about 2% is just kind of dissolved in the blood, okay? So that is oxygen. Now let's talk about CO2. Kind of clean this up a little bit. Okay, so CO2, we went through metabolism in our tissue cells, and so we're gonna have a high amount of CO2. What we want for CO2 is we want it to get it out of our system. So we want to exhale the CO2. And CO2, it's a lot more soluble in blood, so we don't need as high of a pressure of a gradient or a gradient difference. So the CO2, what it's going to do is it's just going to diffuse into our red blood cell here. And now the majority of it, about 70% of CO2, it's going to come into the red blood cell, and there's going to be water in our red blood cell as well. And using carbonic anhydrase, we're going to take that CO2 and that water, and we're going to kick out hydrogen protons and bicarb. Okay, so that's the majority of that. So I have that, and then we're going to have a pump here that's going to use chloride. It's going to come in and it's going to kick the bicarb out. So that's the majority of how CO2 will do things, okay? CO2, hemoglobin, it's got 2 different states. It's got a relaxed state where it has a high affinity for oxygen, and it's also got a T state. So CO2, it can bind to this hemoglobin in its T state, and then it can get transported that way. So about 23% of CO2 binds to hemoglobin, and that's how it gets transported. And the other 7% just kind of dissolves in this capillary here, okay? And then eventually we can take CO2, make it into bicarb, and this CO2 here, we eventually kick it off, goes into our alveolus, and then gets exhaled out. Okay, so that's CO2, how it's transported there. Okay, see what's next here. Okay, last thing we're going to talk about is the hemoglobin saturation curve. So like I said here, hemoglobin's got 4 different binding sites for oxygen, but it's also got 2 different states. It can be in that relaxed state where it has a higher affinity for oxygen, and it's also got a T state where it has kind of a higher affinity for other things, or other things will bind to it, making it less saturated than oxygen. But we want it to be higher in oxygen here, so we get more to the tissues. So this curve, we have O2 saturation on our y-axis, and then pressure of oxygen on our x-axis. So normally what's going to happen, as we have a high pressure of oxygen, we're going to have a high saturation of oxygen. And so what that does, it makes a higher pressure gradient, so we're gonna saturate our hemoglobins more. And then we can decrease pressure, but that hemoglobin is still gonna be very saturated. At some point, the pressure is gonna be so low that we're gonna have a gradient that's gonna kick the oxygen off the hemoglobin into the tissue cells. And that's when our O2 saturation of the hemoglobin will drop. But there's a few things that can affect this, or how it goes into that T state. So one thing, let's do this. So this would be like, if our O2 saturation was lower, this is gonna be our T state, so our 10th state. When that, essentially what's happening is that hemoglobin, it goes through a conformational change and kind of wrecks its affinity for oxygen. Or we have our relaxed state, where our O2 saturation is gonna be higher all the time. So this is gonna be our R state. Excuse me. Okay, so kind of some things that can affect that. Let's talk about T state first. If we have a high hydrogen concentration, that's going to cause it to go into the T state and drop our O2 saturation. And what's happening there is, again, these hydrogen ions, they're binding to the hemoglobin, causing that 10th state. And when the 10th state happens, it doesn't have a high affinity for oxygen, therefore it's not getting saturated as much. So high hydrogen ions will do that. Again, if we have like a low pH, which is essentially the same thing, they're all kind of correlated. Low pH means high hydrogen protons. High hydrogen protons means this hemoglobin's going into T state, and it's going to lower that ability or that affinity to oxygen. Another thing is if there's high CO2, cause the same thing. Just if there's high CO2, it's going to bind to this oxygen, cause it to go in its T state. That's kind of the same story as here. Also, if we have high temperature, it'll cause that. And there's also something called 2,3-BPG. What that is essentially, it was like 1,3-BPG, but then we had an enzyme called 1,3-BPG mutase in glycolysis that changed that to 2,3-PPG. And what that does is, this is like a polar molecule, so it'll bind to this, to our hemoglobin that's got these non-polar aspects to it, or maybe it's the reverse, but either way, it'll bind to that, and again, it causes that conformational change to T state, so it lowers its affinity for oxygen. So if we have a high concentration of that, it's going to cause that T state, which is going to cause our O2 saturation to go down. I think that's it for that. And then exercise also does this, just because you're working hard. And essentially the reverse is true for our R state. So if we have low hydrogen, it'll have a higher affinity for oxygen. If you have high pH, so more basic, also have a higher affinity for oxygen. Low CO2, low temperature, low 2,3-BPG, and then if there's no exercise, you're going to be in that relaxed state there. So that's how this change occurs, and that's it for today. Thank you.